In this video, we're going to discuss how to find some exact values for inverse trig functions, where they're defined. We're also going to discuss how to solve some trig equations. First, looking at the inverse side of things, just to tweak the directions here a little bit. We're going to have some fun with this and try to find all possible answers that could be true for these inverses on the interval from 0 to 2 pi. So kind of keep that in mind as we go. If I'm asked to find the inverse cosine of 1 over root 2, first thing I might take note of is this is a positive 1 over root 2. That means I am working exclusively in two quadrants. I'm working in the first and the fourth quadrants because that's where cosine is positive. Therefore, I'm going to have two answers as possibilities here. Also, since I'm working with cosine, cosine I know is adjacent over hypotenuse. If I sketch out a triangle here, label one of my angles x. If I let the adjacent side to x be 1, the hypotenuse root 2, what should stand out to me is that that is a 45 right triangle because this other side would be 1, making this x 45 degrees. Since I'm working on the interval 0 to 2 pi, I would like my answer in radians. So 45 degrees converts to pi over 4. Pi over 4 would be a value in that first quadrant, so I've got the first quadrant taken care of. As far as the fourth quadrant is concerned, well, I need a pi over 4 value that comes from the fourth quadrant. To find that value, I would need to be familiar with the unit circle. And if I am, 7 pi over 4 would be the value that I go with for that fourth quadrant. So pi over 4 and 7 pi over 4, that would be all the possible answers that could work here for the inverse cosine. I'll try another example. This time we're going to take the inverse sine of 1. Well, staying consistent here, starting with the fact that 1 is positive, consider your quadrants that you're playing with. Talking in terms of sine, first and second would be quadrants where sine is positive. So trying to build a triangle that works for this 1, which is plugged in, once again giving myself an angle x right there. As a ratio, 1 is 1 over 1. Talking in terms of sine, we're looking at the opposite over the hypotenuse. If I try to build that triangle, opposite x would be 1, hypotenuse would be 1. We should notice right away no such triangle exists. Now, that doesn't necessarily mean we don't have an answer. In fact, when you're working in terms of sine and cosine, and you look at the number that's being plugged in right here, as long as that number falls between -1 and 1, we're going to be able to find an answer. Since the triangle approach doesn't work, we have to use the unit circle. So if I set up the unit circle, I've got to revert back to what I know about the definitions for my unit circle stuff. Sine goes with y. So where is y equal to basically this 1 right here on the unit circle? Well, that would be true in one place, up here, where the point is 0, 1. And the radian value that was consistent with that point, that was pi over 2. So pi over 2 would be my only answer for part B here. Part C, let's try a tangent problem. Let's take the inverse tangent of -1 over root 3. Like we've done on the two previous problems, I start with the sign on the value that's being plugged into the function. That is negative. So as you consider what quadrants we're working in, again, we'll have two answers for this one. If it's negative, because tangent, well, let's see, tangent is positive in the first and the third, so if it's negative, we must be working in the second and the fourth. We've narrowed our answers down to those two quadrants as possibilities. We know that tangent as a ratio goes with opposite over adjacent. So I set up my triangle to match the ratio which has been plugged in here to the inverse function. Once again, labeling one of my answers, or one of my angles rather, as x. Opposite x would be 1. Adjacent to x would be root 3, meaning this hypotenuse has to be 2 because this is a 30-60 right triangle. If x is opposite 1, that makes x 30 degrees. 30 degrees converts as a radian measure over to pi over 6. Now, pi over 6 would be an acceptable answer if we were in the first quadrant, but we are not. So we must take the pi over 6 answer that's in the second. That would be 5 pi over 6. And the pi over 6 answer that's in the fourth. That would be 11 pi over 6. So to get these answers again, you got to be familiar with the unit circle. All right, kind of doing these out of sequence with how they're presented for our class here, but let's do part E first. Take the inverse sine of 2. Now let's go back to the tip that I gave back here on part B. That tip was anytime I'm working on this interval of -1 to 1 in terms of values that I'm plugging into the inverse, if I'm talking about an inverse sine or cosine, if I'm plugging in values from this interval, I'm going to get an answer back. But anything from outside this interval, I'm not going to have any approach that works. Triangle stuff won't work. Unit circle stuff won't work. So if you notice you've got a value for inverse sine or inverse cosine you're plugging in that is outside the interval -1 to 1, you can simply cut to the chase here and say, you know what, that answer does not exist. So that's a pretty quick and easy one as long as you recognize what's going on with the number we're plugging in. Okay, now if I do a different type of inverse problem, one where it would be required to sketch out a triangle that is not necessarily a special one. Usually you see an example like this when you're combining functions like we have here on part D. We're taking the sine of the inverse cosine of 5/13. All right, when we start combining functions, we work with the innermost stuff first. And thinking of how we approached the previous problems, you've got this inverse function right here. Think about how cosine in this case connects to this ratio. It would be the adjacent over the hypotenuse value. Sketch out a triangle where you label an angle measure x, let the adjacent side be 5 and the hypotenuse be 13. If you can determine what this side is over here, obviously that side would be opposite. And with where you're going, trying to find the sine, well, sine is opposite over hypotenuse. If I know this opposite side would be 12, then 12 over hypotenuse 13 would be my answer. And that opposite side would have to be 12 because if you think about it, you got a Pythagorean triple of 5, 12, and 13. And if you didn't know that, then I would take 5 squared plus pick a variable, maybe a squared equals 13 squared. Solving for a, you would also find that you get 12. All right, for the final few examples that I want to cover here where we're solving trig equations, basically we're going to bring a lot of ideas together. We're going to bring together some algebra concepts and algebraic approaches that we use anyway to solve equations. We're going to use what we know about identities. We're also going to use what we know about applying inverse trig functions. So in a problem like I have here in part A where there's only one trig function to play with, one variable plugged into that trig function. What I want to do first is I want to isolate this unknown expression, this trig function. To do that, I'm going to add 1 over, and then I'm going to divide by the 2 in front of the expression. So I get cosine squared of x equals, obviously 0 and 1 is 1. Dividing by that 2, I get 1/2. Now I'd like to be able to isolate this cosine of x as much as possible. So if I take the square root of both sides, I can eliminate that squared part. Cosine of x is going to equal 1/2. But remember, when you're taking a square root of both sides and solving, you need the plus or minus. As I take the square root of this fraction, to clean this up just a little bit, I'd have the cosine of x equals plus or minus square root of 1, which is 1, over square root of 2. Now that I've isolated the trig function, I'm going to drop the cosine of x out. I'm going to drop it out because I can apply an inverse to both sides. When I do that, I'm taking the inverse of this other side. Now, applying what I know about inverses, the first thing I do is I consider these signs right here. Since it's plus or minus and we're talking about cosine, well, that means we could be working in any quadrant, because we've got our positive cosine quadrants here, we've got our negative cosine quadrants here. So we're going to have 4 potential answers for what x can be. And since I also know that cosine goes with the adjacent over the hypotenuse ratio, setting up a right triangle to use, letting my angle here be x. The adjacent would be 1, the hypotenuse would be root 2. If I complete the other side, which would have to be 1, I know I'm working with a 45 right triangle. So x is going to be 45 degrees. As a radian measure, that would be pi over 4, and that would take care of this first quadrant. The other pi over 4 values I would need would come from the second, third, and fourth quadrants. So in the second quadrant, that would have to be 3 pi over 4. In the third quadrant, that would have to be 5 pi over 4. And in the fourth quadrant, that would have to be 7 pi over 4. So there are my 4 solutions to this equation. All right, if you look at this example here, what should stand out is that you've got 2 different types of trig functions to work with. Usually when that happens, that means at some point here we're going to have to do some kind of factoring. And the only way we can ever do any kind of factoring, if we're going to solve an equation, is if we have everything moved to one side. So let's start by subtracting the 1 over. I have 2 cosine squared of x then, plus sine of x, minus 1 equals 0. If you look at what we have now, it kind of takes on this quadratic looking form, but we really can't use the quadratic kind of form here to factor because we've got different trig functions. So whenever you have different trig functions, try to create a scenario where you just have one function to work with. Notice this cosine squared of x here. If I'm trying to change everything over in terms of one function, maybe I could use an identity. Identity for cosine squared of x would be 1 minus sine squared of x. So if I substitute that in, so here I am replacing cosine squared of x with 1 minus sine squared of x. By doing that, everything now will be in terms of the same kind of function, being the sine function. Oops, looks like I forgot a little x right here. Okay, after doing that substitution, again, I've got an equation to work with. I got some parentheses, so I want to clear the parentheses by distributing. If I distribute that 2 through, obviously I will get 2 here when I multiply. Now, eventually, I'm going to combine like terms, so I've got a 2 here when I multiply with this minus 1. 2 minus 1 would be positive 1. I'm going to go ahead and stick this positive 1 here at the end. So I'm kind of doing 2 steps at once. I multiply the 2 and the 1, get 2. Subtract the 1 here, get positive 1. All right, going back to the distribution, I got to take 2. I got to multiply to this negative sine squared of x. I'd have negative 2 sine squared of x. The other thing we need to bring along at this point that hasn't been considered from that step is the sine of x, so I'll bring that down. Meantime, this all equals 0. Now, if you look at this form, I was talking about maybe having a quadratic form back here at the second step. We weren't quite at a quadratic form. because of the different functions. But now if I look down here, I got the same kind of function I'm dealing with, so this would be a quadratic form. The only thing I'm not a big fan of is this negative lead coefficient. So I might do a little trick here where I change all the signs, and by changing the signs, in reality I'm multiplying everything by -1. That would give me 2 sine squared of x minus sine of x minus 1 equals 0. Well, now if I take what I know about quadratics when they all equal 0, and I'm trying to solve this kind of equation, and I look at a quadratic form, like suppose I have 2a squared minus a minus 1 equals 0 instead. You know, off to the side, I could introduce this variable of a.
Attention teachers, the learn.
Anyway, sorry for that interruption. That happens sometimes when I do these pre-recordings. But as I was saying, you look at this quadratic form and you try to simplify things a little bit, maybe take the trig function part of it out and introduce an a in its place. I get an equation like I have right here, where if I try to factor and solve, I take note of what this factors to. I've got 2a squared, so it'd have to be 2a times a. I've got 1 here, so it has to be 1 times 1. To make that work, if I make this positive and this negative, then my outside I'll have negative 2a. My inside I'll have positive 1a. That would give me a negative 1a back. So that's my factored form. I take each factor, set it equal to 0, and solve from here. Well, let's see, over here a equals 1. For this equation, 2a, if I subtract 1 over, would equal negative 1. Divide by 2, a is negative 1/2. So off the side here, I've done a little side thought. I take this work, and I let a replace basically my sine stuff over here. So I could let now the sine of x equal, well, 1a equaled negative 1/2, so I'll let that equal negative 1/2. And I could also let, since this a equals 1, the sine of x equal 1. Where we're ready to drop the sine stuff, so to drop the sine stuff, we take the inverse of each side. Since I was running out of room there on the previous slide, I've just transferred over that step here to this new slide. We'll consider each of these equations now, starting with the first. If I'm talking the inverse sine, and I know that I've got a negative plugged in, where the sine function is negative would be down in the 3rd and 4th quadrants, so I know my answers will come from those 2 quadrants. I know sine is opposite over hypotenuse, so as I set up my right triangle, and I set up my angle x, the opposite side would be 1, the hypotenuse would be 2. Fill in the other side, that would be root 3, making this a 30-60 right triangle, so x would have to equal, since x is opposite 1, x would be 30 degrees, or pi over 6. But remember, I'm working down in the 3rd and 4th quadrants. So if I take the pi over 6 value that's down in the 3rd quadrant, knowing what I know about the unit circle, that would be 7 pi over 6. And from the 4th quadrant, that would be 11 pi over 6. So I've got 2 solutions so far. Now considering this other equation, where notice I have a positive 1 that's plugged in, this would be an example where if I try to set up a right triangle, it doesn't work. However, this 1 does fall within our little domain over here of negative 1 to 1, so we know it has to work, and since the triangle approach will not work, we've got to use what we know about the unit circle, and we've got to take the y values from that unit circle where we have a 1 at that point. The only place that's going to be is up here, where our point would be 0, 1, and at that point, the radian measure would be pi over 2. So in the end here, we have 3 solutions to the original equation. All right, if we look at one more example here where we're solving a trig equation, and we consider what we did on the previous example, because what we did on the previous example, we had 2 different trig functions to work with. We had the same kind of scenario here. What seemed to work out for us, at least initially, was moving everything to one side. So I'll do that on this problem as well. I'll keep my tangent of x, sine of x on the left side, and bring over this negative root 3 of sine x. When I bring that over, I would be adding the root 3 sine of x over. So all that equals 0. Okay, at this point, you are trying to get to a situation where maybe we only have the one trig function to work with. But something that should stand out here, because really we've got 3 trig functions sitting in here, 2 distinctive types. Notice that you have a sine of x and a sine of x that are common here between these 2 terms. So I might take a sine of x out. Ultimately on that previous problem we did some factoring and that seemed to work. In this case we could use a greatest common factor idea, take the sine of x out, and then you'd be left with, well, sine of x comes out of this first expression, tangent of x would be left, plus, take sine of x out of the second expression, you'd be left with root 3. So now we have something in a factored form and it equals 0, which is significant. We could take each factor, set each factor equal to 0, and we could solve. So the sine of x is one factor, set that equal to 0. Tangent of x plus root 3, another factor, set that equal to 0. For this left equation, we're ready to drop the sine out since the sine of x is isolated anyway. We do that and we're introduced to an inverse sine of 0, where if I have 0 plugged in to my inverse, then triangles definitely will not work because we don't have side measures of 0. Sine is consistent with the unit circle and all the y values. So going to the unit circle, looking at the y values and where they may equal 0, we would have a couple of points here. This first point, we'd have 1, 0. At this second point, we'd have negative 1, 0. So since y is 0 at each of those points, and our answers here are restricted from 0 to 2 pi inclusive, well, x could equal, at this initial point, we'd have 0. As we work our way around to this other point, we'd have pi. And as we come back to the beginning here, to this first point, that's also 2 pi. Again, it was 0 to 2 pi inclusive. We could include all 3 of these values as answers. Now, in the meantime, we've got this other equation on the right side. We've got tangent of x that first we would want to get by itself. So subtract root 3 over. Tangent of x is isolated, so now apply the inverse to each side to drop that tangent out. We'd have the inverse tangent of negative root 3. This is one where it looks like triangles would work because we'd have a ratio of negative root 3 over 1. We'd also appreciate that we do have the negative here. So since we have a negative there, and we're talking in terms of tangent, tangent would be positive in the first and third quadrants, so it'd be negative in the second and the fourth. Those are the 2 that we take. Looks like we're going to have a couple of answers then. If we draw out our right triangle, label an angle measure x. For tangent, we're talking opposite over adjacent, so opposite would be root 3, adjacent would be 1. If I fill in my other side measure, that'd have to be a 2 because this would be a 30-60 right triangle. And if I'm trying to determine what x is going to be, well, let's see. X is opposite root 3. So x would have to be 60 degrees. If it's 60 degrees as a radian measure, we're talking pi over 3. But we can't use pi over 3 because that's in the first quadrant. Therefore, we need the pi over 3 value from the second. That would be 2 pi over 3. And we need it from the fourth as well. That would be 5 pi over 3. So for this example, we've got 5 possible solutions for what x could be.